This is a review of Exit Slip 15, where we spent a little time working on graphing exponentials and talking about their applications. The first question asks us to consider the function f of x equals 1/3 to the power of x plus 1. The domain of all exponential functions is negative infinity to infinity, so the domain here is kind of a freebie. The range, however, will depend upon whether the graph has been transformed at all. Specifically vertically, has the graph been shifted up or down? So using our knowledge of transformations, we can see that this graph has been shifted up by 1 unit. So the range of the graph would be transformed from 0 to infinity from the base graph to be 1 to infinity. So that vertical shift takes the base exponential graph and shifts the range up by 1 also. So with this in mind, to actually sketch the function, we can do a couple different things. Sometimes what I do is just graph the base graph and then pull all the points up by 1. Maybe that's how I'll show it here. Or if you prefer, you could just build your table based on the actual function. So I'm going to consider the base graph, which would be just y equals 1/3 to the power of x without that plus 1. And I'll just make a simple table of values. We've discussed how it's probably good to have like 2 negatives, 0, and 2 positives. So I'll just do -2, -1, 0, 1, and 2. And then I'll find the corresponding y's by just taking each of my choices for x and popping it in as the exponent. I'll leave it to you to verify each of these y's, but 1/3 to the power of -2 will give me back 9. 1/3 to the power of -1 will give me back 3. Anything to the power of 0 will give me back just 1. 1/3 to the power of 1 is 1/3. And 1/3 squared, 1/3 times 1/3, would give me back 1/9. So I'm able to generate 5 ordered pairs that I'll then just plot for you here. And that should be a pretty good base graph sketch. So let's see, I'm going to need space in the x direction to go between -2 and +2. And then in the y direction, I'm going to need to be able to go all the way up till 9. So I'll just show that real quick here. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so my base graph would be when x is -2, y is 9. When x is -1, y is 3. When x is 0, y is 1. When x is 1, y is 1/3. When x is 2, y is 1/9. So I'll just go ahead and sketch in that base graph, something like this. So when the base is a fraction, we know it will decay rather than grow as x gets larger. But now the actual graph we've been asked to graph for the exit slip was a transformation, meaning it got shifted. Specifically, it got shifted up by 1 unit. So I'm just going to take all the points that I have plotted and pull them up by 1 unit. So I get -2, 10 instead. I'll get -1, 4. I'll get 0, 2. I'll get 1, 1 and 1/3, and then I'll get 2, 1 and 1/9. So the actual graph that I'll be looking for will be this orange graph here, which is all the points we plotted for the base graph, just pulled up by 1 unit. Your strategy for building that graph may have looked a little different than mine, but as long as we have those same points in the end, that's what I'll be looking for. So the orange graph shows 1/3 to the power of x plus 1. The second part of the exit slip looks more at the application side of things. So we're asked a little bit about a person investing. They make an investment of $2,125 into an account that's earning 9% per year compounded continuously. So when we hear the word continuously, we should know right away that we're using a particular formula. We learned 2 different formulas for investing money. One was A equals P times 1 plus the quantity R over N to the NT. And then we also learned a little bit about A equals P E to the RT. So the difference between these formulas is the one on the right side of the screen is what we use anytime there's continuous compounding. So that's what we're working with in this problem. So I'm going to set up that A equals PE to the RT here. I don't need the formula on the left because that would be if we were compounding a specific number of times within a year, like quarterly or monthly. So let's take this one away for now and just work with A equals P e to the RT. I just like to start by writing down the formula I'm using, and I often on the side will just jot down the variables so I can fill in what I know and what I am looking for. So let's see what we know. In this case, we're investing $2,125, which is the principal, the amount that we make the investment for. The rate in this problem is given as 9%. We always write our rate as a decimal. So 9% would be 0.09. And then we're asked about how much money will be in the account after a 2-year time span. So that means t is equal to 2. Time is 2 years. So with that in mind, it looks like the only unknown is how much money we're going to have down the road, and that's what the question is asking for. How much will we have? So let's plug in what we know and see what we can find. So A will equal our P value of $2,125 times E to the power of R, which is 0.09, times the amount of time in years, which was 2. So this is ready to pop on into your calculator. I'll just pause and punch this into Desmos and come back. You guys can do the same thing either on your calculator or Desmos, and we'll provide an answer rounded to the nearest cent for this problem. How about? Be right back. Okay, so I just used Desmos to punch my numbers in, and I'm getting back about $2,544. And let's go ahead and, like I said, round to nearest cent for this one. I know on the exit slip sometimes I'm not super specific on rounding, but if I did go to nearest cent, it looks like we'd say 9 cents. So in the homework or quizzes or different things, if rounding really matters, just pay attention to the directions. So sometimes we round to the nearest cent, sometimes nearest dollar, but for this one, how about we just go nearest cent? So this would be the amount of money we have 2 years down the road based on the information we're given.